Right. Good morning, friends. In this session, I'll be discussing about the topic X-ray tubes. Okay, and in this session, we'll be understanding how the structure of the X-ray tube and the important points regarding the X-ray tube. Okay, so let me read the points written here. It's written that we have something known as cathode, and it is negatively charged electrode, and the filament is made up of tungsten emits electrons, and you have something known as thermo-ionic emission, and there's a production of electrons. And it's also written that you have something known as anode, and that is a positively charged electrodes, and the target is made up of tungsten, and the purpose of anode is it receive the electrons and generate the X-rays. So let us understand what is it trying to tell us. So if you look into the structure of this X-ray tube, we need to understand that this is a negatively charged cathode and this is a positively charged anode. Now, if you observe carefully, you have a filament here, guys, and this filament is made up of tungsten. Remember, okay, and this filament is made up of tungsten. This filament is made up of tungsten. Filament is made up of tungsten. And what does this filament does? So this undergoes there's something known as thermo-ionic emission. Due to the thermo-ionic emissions or thermo-ionic emission, in the sense it is an emission of electrons by the heat, okay, by the heat. So this a tungsten, this filament, it starts emitting the electrons. Remember, it starts emitting the electrons. Starts emitting the electrons. And these electrons, what they do is, and it goes or it moves into the towards the anode. When it moves towards the anode, you have this is also made up of tungsten, okay, and these electrons hit this anode and they generate X-rays. They generate X-rays. So that's the basic point. It's written. And now let us understand. You have got something known as Brem-Strong reaction, and you have got something known as characteristic radiations. Say example, if this is the nucleus, right? Nucleus of an anode. You can look into the points here. The electrons which are coming from the cathode, they are traveling, and remember that they divert the path suddenly towards this side. Okay, they need to go into the straight line, but near the nucleus, they divert their path. Soon after the diversion of their path, remember this reduction in the speed, in the sense, say example, if they are going in a speed of 100 kilometers, okay, just example, like a bike, right, 100 or 200 kilometers, suddenly they reduce to the 100. So from 200, if they reduce to the 100 suddenly speed, there is a loss of energy, and this loss of energy is in the form of photon, that is X-ray, right? So that's a basic point. So ultimately we need to understand they deaccelerate and they loses the energy. They deaccelerate. What loses? The energy deaccelerate and they loses the energy, and loss of energy is in the form of photon, that is X-ray. Now you need to understand, I have explained you, right, regarding this cathode, anode, all this, and I told you regarding the Bremsstrack reaction and characteristic radiations. Now, the most important interaction in all the X-ray tubes is this Bremsstrack reaction. It's nothing but where the energy, okay, the reaction happening at the nucleus is Bremsstrack reaction. the radiation which are coming from the orbital shell, it is a characteristic radiation. All the X-ray tube, they follow the reactions or the Bremsstrahlung reactions, except the mammography tube, they have or they go undergo this characteristic radiations. Remember this, okay? Characteristic radiation. So, what is this characteristic radiations? Now, now now the electrons are moving, you're gonna hit this atom, right? You got a shell, KLMN shell. Now, soon there is a loss of electrons in the inner orbits, okay? The outer orbit try to occupy the inner orbit. During the path or during this when these electrons occupy from the outer orbit to the inner orbit, they start releasing an energy, right? And this energy, they're in the form of photons, right? They're in the form of photons, the X-rays. So ultimately, one important point, most important interaction happens in this X-rays is this Bremsstrahlung reaction, except the mammography tube where you have characteristic radiation. Okay, so let us continue the session. Okay, let us continue the session. The same point. Now, what is it trying to tell us? What's happening with the X-rays? Now, these are the basic which we need to understand regarding X-rays. Say this is a body tissue. Now, these X-rays which are generated from the anode, it passes through the body tissue. Right? You have a film, okay, Castle, X-ray film, and you have something known as AGBR. Okay, now the one point is, if you look into the structure of the X-ray, right? This is an either end of the X-ray, right? From the superficial or to the deep. This, you have got something known as super coat, you have emulsion, and you have adhesive layer. In these X-rays, especially in the emulsion layer, you have silver bromide which is present in this aspect. Whenever the X-ray passes through the body tissue, then it interacts with the silver bromide of the X-ray and they give a color of black. So whenever there is an X-ray, the air, we look into this, the presence of air that gives a black color. Why does it give a black color? Because this air interacts, or the X-ray passes through this air. There is no blockage. Say example, the X-rays are passing through the lungs. Lungs are made up of air, they are filled with air. So the X-rays pass through that air, and these X-rays, they interact with the silver bromide. Soon after they interact with the silver bromide, remember that it gives a black color, right? Now the next important aspect, the X-rays, they give a black area. Remember that air anywhere, emulsion, you have a super coat, you have an emulsion, and you have an adhesive. Okay, so that's a basic point. In the next important aspect, that is an pneumoperitoneum. Say example here, you have got an X-rays. Okay, you got an X-ray or a black spot which is present below the left lung, and that is common, it's a stomach. If the same black spot or the black which is found, if it's found in the right dome of diaphragm below the lungs, it is because of pneumoperitoneum. So that is how you can differentiate it. Okay, so ultimately at the end we need to understand, during the X-ray, when it passes through the air, when it hits the silver bromide in the X-ray, it gives a black film. Now let us understand. Now say example, if the same X-ray pass through the bones, since the bone is white color, okay, white. Now if it passes through the bone, it gives a white color. Now, how do you tell it is a white, it is a bone or a stone? Say example, if the white color is in anatomical position, okay, is in the anatomical position. Say example, you are taking the X-ray of a leg, and if the white is present in the layer space where the tibia and the femur is present, guys, so that is an anatomical location. Now, say example, how do you differentiate that's a stone? Stone, it is in the non-anatomical location, right? It's a non-anatomical location. The non-anatomical location stones can be present in the lumen, can be present in the tissue. If it is present in the lumen, guys, it is a calculus. If it is present in a tissue, it is a calcification. Now, if it is present in the lumen, right, or any bile tract or urethra or such lumens, it can be in the shape of round, it can be shape in oval, it can be in the shape of lumen shaped, okay, it can be in the shape of lumen shaped. Now, say example, if the stone is present in the tissue, right, and that is a calcification. In the lumen, you can see that is a calculus. If you look into the stones which are present in the tissue, we call it as calcification. The calcification can be punctate, the calcification can be irregular, calcification can be like organ shaped, okay, it can be organ shaped. It can be an organ shaped. It can be a calcification of an organ. We can look into this. We have got a question here 2024 where it is a pancreatic shape. And you can look into this. This is an irregular shape. This is a punctate. So ultimately we need to understand, right? The X-rays, they show white because of if there is a bone. How do you find it is a bone? It is an anatomical location. How do you find it is a stone? It is a non-anatomical location. Now, the next point, once it is a non-anatomical location, we need to look into this whether the white or the stone is present in the lumen. If the stone is present in the lumen, you call that as calculus. If the stone is present in the tissue, we also call that as calcification. Now, this stone which is present in the lumen, guys, and it can be in the shape of round, it can be shape of oval, it can be shape of lumen. If these tissues, right, if this calcification is present in the tissues, and we can find that as a punctate type, irregular type, like you can take the shape of an organ, right? That's all you need to understand. Now let us understand. Say example, you have got something known as grayish white, and the color on the X-ray, if you have the grayish white, and this is any other than bone or air. Say example, if the grayish white, it can be because of muscle, it can be because of tumor, it can be because of blood, you can see because of pus. So it can happen, okay, it can happen anywhere in the blood, tumor, pus also. So ultimately, for timing, we are understanding that there are three densities. One is air, which is black, next is bone, which is white, and you have soft tissue density that we spoke about, the grayish. But apart from these three densities, we need to understand there are other two densities, but not so important for the NEET PG, that is a fat and the metal. Okay, so total 5. So that's all about the three densities, right? That's all about the three densities in the X-ray. Now, let us understand a basic two important topics or the points here. That is KVP, next is MAS. And what is KVP, guys? Remember and understand, it is a kilovolt peak. Now, what is it, KVP? It is a voltage, right, supplied across the tube. How much voltage is supplied across the tube is the voltage. It is a kilovolt peak. Okay. Now, this voltage is directly proportional to energy. More the voltage, more the energy. And this voltage is directly proportional to the penetration. More the voltage, more is the penetration. When I tell you bit about now, when I speak about the KVP, when I tell you about the voltage, it is directly proportional to the energy, it is directly proportional to the penetration. And when I tell you about this kilovolt peak, that is a voltage that is supplied across the tube. Now the next important aspect, that is MAS, that is milliampere second. Okay, when I start speaking about the milliampere second, remember this, guys, it's very important to understand. Whenever I speak about the milliampere second, okay, whenever I speak about the milliampere second, what is milliampere second? It is the current into exposure time, right? It is current into exposure time. So 2 points you are going to consider, that is a current and the exposure time. And it has got MAS has got, and that is milliampere second, has got no effect of energy, has got no effect on penetration. But one thing, it is directly proportional to the number of X-rays per unit area. That's a basic point. Okay, that is number of X-rays per basic area. It has got no relation with the energy, no effect on the penetration, no effect on the energy. It tells about the number of X-rays per unit area. Now say example, you have given the example here, right? You have got an example. Now there is a beam of 100%. A patient is lying here, right? And the patient, the 20% is absorbed by these patients. Okay. So the background, if you look at the background, the beam which is passing just behind the person is just an 80%. Because it has to pass, right? It has to pass through this, pass through the soft tissue or bone or such, pass through the person. Now if you look into the surround at the ends, okay, where the beam is not interrupted by this person. When this beam is not interrupted by this person, the amount of energy beam which is present or which is supplied, the same amount of energy it is falling on the background. Now say example, you have got an 100% beam which is present here. The same 100% beam, it's falling on the background, right? Now if you look into the difference here, right, it is 100, this is 80 here, and that is a difference of 20%. Now let us understand, and what is the name of this 20% and what do we call? And that 20% is the difference, and that we call that as contrast. Okay, now let us understand. Say example, you have increasing the kVp, that is kilovolt power. When there is an increase in the kVp, ultimately I have told you, it depends on the energy, it depends on the penetration. So increase in the kVp leads to the increase in the penetrating power, right? Now instead of 80%, say example, once I start increasing the penetrating power, and this leads to 90% beam will reach the X-ray. 90% beam will reach. Ultimately you need to understand, now the difference is now 90%, 90, right? Now difference is 10%. So the contrast, before it was 20%, now the contrast is 10%. The contrast is decreased, means when there is an increase in the kV, that is the kilovolt power, there is increase in the kVp, there is a decrease in the contrast. So ultimately, can I tell the contrast is inversely proportional to the kVp? Do you agree? Yes. And the next important aspect, next important point, say example, now there is a block of 40%. Okay, so 40% in the sense, on the background you have got a 60%, and surround you have 100%, 40%. Remember, now the contrast, the difference is increased, contrast is increased. When I tell contrast is increased, so it is inversely proportional to the kVp decrease. When kVp decrease, there is a decrease in penetration. Now what is the standard kVp in the chest X-rays? Remember, the standard kilovolt power, the X-rays is, the standard is 60. Okay, sorry, peak, kilovolt peak, that is 60. Let us look into the next important points, that is MAS, milliampere second. Now say example, what is the milliamperes? Number of X-ray per unit area, right? Now say example, now before it was 100 beam, now I have increased the MAS, that is milliampere second, where from the 100 I have increased to 200. When I increase to 200, say example, 20% is absorbed by the person who is lying between, and the X-rays which is falling on the background is 160. Okay, and the one which is going at the periphery, it is at 200. So if you look into this 200 and 160, the difference is 40. So ultimately the increase in the MAS, milliampere second, so there is increase in the contrast. So ultimately the milliampere second is directly proportional to the contrast. Now let us end the session by speaking about the three important questions. The first question is, contrast in a radiograph can be increased by, since it is a directly proportional to the MAS, so it is increased by MAS. Now ultimately the next important aspect, contrast in a radiograph is predominantly dependent on, it is predominantly dependent on. Now they have given the option like KVP, they have given the option of MAS, they have given the option of exposure time and tube current. So the tube current is KVP, right, and exposure time it is MAS. The contrast is in radiograph is predominantly dependent on. So if you look into this, okay, this is an X-ray which tells about this is a lungs, you have an surrounding background. KVP change contrast by changing the image, okay. So the KVP changes the contrast by changing the image. The ultimately the background is same, okay. MAS that gives about the background, and KVP that gives about the imaging point. They give about the imaging point. So the image more important point, okay, more important image, more important than background. Image more important than background. So ultimately we need to understand the contrast in a radiograph, okay, is predominantly dependent on KVP. Why it is predominantly dependent on KVP? Because the KVP changes the contrast by changing the images, okay, changing the image. Background is same, changing the image. So ultimately KVP is answered. The next important aspect, contrast in a radiograph can be increased by. So what all factors? One is increased, either you go contrast in the radiograph can be increased by what? By what is important. So either the increase MAS, okay, increase MS. The first factor that should be modified to image a highly built patient is KVP. Heavy built patient is KVP. Heavily built is KVP. Contrast in the radiograph can be increased, okay, can be increased by, okay, that is the next, you have got a next question. But remember this. Now say example, you are gonna take the X-ray of an heavily built patient. For the heavily built patient, you need to look into the penetration should go well. So penetration of the beam. So higher increased penetration happens when there is an increase in KVP. Which factor should modify to improve the contrast in the base? That is increased KVP. Remember, it is an increased KVP, right? Increased KVP. So whenever to modify, okay, when I speak about the modification point, in obese patient, right, in obese patient, you have an options, okay, whether what happens here is decreased KVP or increased MAS here, because we're going to improve the contrast here. To improve the contrast is inversely proportional to the KVP, directly proportional to the MAS, correct? So in the option which we need to avoid here is decreased KVP. Why we need to avoid decreased KVP? Because it's an obese patient. So if the KVP is decreased penetration. So the next option is increased MAS. So this will be the option, okay, this is the correct answer. Which factor should be modified to improve contrast in the obese patient? It is increased MAS. That's all for now, guys. Let's look into the next session later. Thank you.